Imagine a room perfectly sealed and completely empty. No light, no sound, no air, just pure, unbroken emptiness. Yet in this void, something profound is at work, something unseen but undeniably present. This is the paradox of nothingness. What appears to be nothing is, in fact, filled with the potential for everything. Nothingness is not merely a void. It is the quiet stage upon which the drama of existence unfolds. It is the space between the stars, the gap between thoughts, the stillness that gives meaning to motion. In the silence of the void, we find the echoes of the universe's most profound secrets. To understand nothingness is to step into this hidden world, where the absence of things reveals the very fabric of reality. It is an exploration that challenges our perceptions and invites us to see the universe not just as a collection of things, but as a complex interplay between what is and what is not. This journey into the heart of nothingness promises to change the way we understand the world and perhaps even ourselves. Nothing and atoms. Imagine, if you will, a time in your childhood when the question first struck you: where did everything come from? This innocent query touches upon the profound mysteries that have puzzled humankind for millennia. In the dawn of our consciousness, we begin to grapple with the notion of nothingness. The enigma of what preceded our birth and what surrounds the universe stirs within us a sense of wonder. This fascination is not new. It echoes through the ages, having tantalized the minds of philosophers and scientists alike. In ancient Greece, the great thinker Aristotle postulated that nature abhors a vacuum. For nearly 2 millennia, his assertion held sway that a void could not exist. This belief persisted until the Renaissance, when the advent of experimental science began to challenge established doctrines. Galileo's students, in a groundbreaking experiment, revealed that the resistance to creating a vacuum was merely the weight of the atmosphere pressing down upon us. This revelation marked a pivotal moment in our understanding of nothingness, paving the way for future scientific inquiry. Fast forward to the 20th century, as humanity reached for the stars. The iconic Earthrise photograph taken during the Apollo 10 mission provided a humbling perspective of our place in the cosmos, a blue jewel suspended in the vast, seemingly empty expanse of space. Yet, the void is not as empty as once thought. Modern physics reveals a complex tapestry woven into the fabric of space. Quantum fields, virtual particles, and the very essence of the Higgs field suggest that even the emptiest regions of space are teeming with activity. Thus, we return to our initial question with renewed insight and deeper appreciation. As we delve further into the nature of nothingness, we find that the quest to understand our origins is a journey that intertwines science, philosophy, and the boundless curiosity that defines our humanity. In the late 19th century, the scientific community was on the cusp of revolutionary discoveries. At the forefront of this transformation was the atom, long considered the indivisible building block of matter. But as scientists probed deeper, they discovered that the atom was far from solid. In 1897, J.J. Thomson, through his ingenious experiments with cathode rays, unveiled the existence of the electron, a minuscule, negatively charged particle. This discovery shattered the classical image of the atom, revealing it to be a complex structure with electrons orbiting a dense central nucleus. Astonishingly, these investigations revealed that the atom is overwhelmingly empty space. The nucleus, tiny and dense, occupies but a fraction of the atom's volume, with electrons whirling around it at vast distances. To put this in perspective, if an atom were the size of a cathedral, its nucleus would be a mere grain of sand. Further experiments by scientists such as Philippe Lenard showed that electrons could pass through seemingly solid matter with ease, reinforcing the idea that atoms are primarily voids. This emptiness within the atom is staggering. 99.999999999% of it is empty space. Ernest Rutherford's gold foil experiment in 1909 provided dramatic evidence of this structure. As alpha particles were fired at thin gold foil, most passed through unimpeded, but a few bounced back, deflected by the dense nuclei. This experiment vividly illustrated the atom's vast internal emptiness and the powerful forces at play within. But the story does not end there. Even the nucleus, thought to be the solid core of the atom, contains within it a further layer of complexity. Protons and neutrons, the building blocks of the nucleus, are themselves composed of even smaller particles known as quarks. These quarks are held together by the strong nuclear force, creating a dynamic, buzzing hive of activity within the seemingly empty nucleus. Today, particle accelerators like those at CERN probe even deeper into the subatomic world, revealing a universe that is both intricate and fundamentally void. The atom, once thought to be a solid sphere, is now understood to be a mostly empty space, filled with electric and magnetic fields that define its structure and interactions. Thus, we uncover a paradox at the heart of matter. The solid objects we interact with daily are, at their most fundamental level, largely composed of empty space. This revelation challenges our perceptions and deepens our appreciation for the intricate dance of particles that make up our universe. Space and waves. Space, the final frontier, is often conceived as a vast emptiness, a boundless void. Historically, space was thought to be a mere backdrop, a passive stage upon which celestial bodies performed their cosmic dance. Aristotle and other ancient thinkers viewed space as a static void, unable to contain anything. However, this perception began to change with the advent of modern science. The Renaissance ushered in a new era of discovery. With the invention of the telescope, Galileo Galilei and other pioneers peered into the heavens, revealing a universe filled with more stars and mysteries than previously imagined. The early 20th century brought a revolutionary shift in our conception of space with Albert Einstein's theory of relativity. Einstein proposed that space and time are interwoven into a single continuum, space-time. This fabric of space-time is curved by the presence of mass and energy, creating the gravitational forces that govern the motion of planets, stars, and galaxies. Einstein's vision of space as a dynamic entity, capable of being warped and curved, transformed our understanding. No longer was space a passive void, it became an active player in the cosmic drama, shaping the very structure of the universe. Quantum physics reveals a teeming microcosm within the apparent emptiness. Space is filled with quantum fields, where particles constantly pop in and out of existence. This quantum foam, as it is sometimes called, is a seething sea of activity that defies our classical notions of emptiness. Moreover, modern cosmology has uncovered the existence of dark matter and dark energy, enigmatic components that comprise most of the universe's mass energy content. While invisible to our direct observation, their gravitational effects are profound, shaping the formation of galaxies and the expansion of the universe. Even the very early universe leaves its imprint on the fabric of space. The cosmic microwave background radiation, a faint glow permeating the cosmos, is a relic of the Big Bang, providing a glimpse into the universe's infancy and the subsequent evolution of space itself. Thus, as we delve into the nature of space, we find that it is far from empty. It is a complex, dynamic, and ever-evolving entity, filled with fields, forces, and particles that shape the universe on both grand and minute scales. In ancient times, philosophers like Aristotle postulated the existence of a medium called the ether, an invisible substance that filled the universe and carried light waves. This ether was thought to be the fundamental medium for wave propagation in the cosmos. The nature of light became a central question. Was it a particle or a wave? Experiments by scientists like Thomas Young, with his famous double-slit experiment, demonstrated the wave-like properties of light, challenging the classical view. The 19th century saw a breakthrough with James Clerk Maxwell's formulation of the electromagnetic theory. Maxwell's equations elegantly described how electric and magnetic fields oscillate to create electromagnetic waves, including visible light. This unified theory confirmed that light is indeed a wave, but the question of the ether remained. The early 20th century brought a dramatic shift with, yes, you guessed it, Albert Einstein's theory of special relativity. Einstein proposed that the speed of light is constant and does not require a medium like the ether to propagate. This revolutionary idea dispelled the notion of the ether and introduced the concept of space-time, a unified entity where waves and particles exist. Einstein's general theory of relativity further expanded our understanding. Space-time itself could be warped by mass and energy, leading to the prediction and eventual discovery of gravitational waves. Ripples in the fabric of space-time caused by massive cosmic events like colliding black holes. The quantum revolution added another layer of complexity. Quantum field theory describes how particles are excitations of underlying fields that permeate space. These fields are the true substance through which waves propagate. Thus, what appears to be empty space is actually filled with these dynamic quantum fields. Modern experiments at particle accelerators like CERN continue to probe the nature of these fields, revealing a rich and intricate tapestry of interactions that challenge our classical notions of waves and particles. The discovery of the Higgs field, for instance, explains how particles acquire mass, further demonstrating the profound structure underlying apparent emptiness. The void, far from being empty, is a vibrant, dynamic medium where waves propagate and reveal the underlying structure of our universe. Traveling on a light beam and the vastness of space. Since antiquity, the nature of light has fascinated philosophers and scientists. From the early musings of the Greeks to the Renaissance thinkers, light has been a beacon of mystery and discovery, guiding us toward a deeper understanding of reality. The 17th century brought significant advancements. Isaac Newton's experiments with prisms revealed that white light is composed of a spectrum of colors. This discovery laid the groundwork for our modern understanding of light, though the true nature of light remained elusive. The dawn of the 20th century marked a pivotal moment in our understanding of light. Albert Einstein, in his groundbreaking theory of special relativity, proposed that the speed of light is a universal constant, unchanging regardless of the observer's motion. This revelation fundamentally altered our perception of space and time. Einstein's theory revealed that as objects approach the speed of light, time itself slows down and distances contract. This phenomenon, known as time dilation, has been experimentally confirmed and forms the basis of our understanding of relativistic physics. In his general theory of relativity, Einstein expanded these ideas to include gravity. He demonstrated that massive objects like stars and planets curve the fabric of spacetime, causing light to bend as it travels through this warped geometry. This bending of light, known as gravitational lensing, allows us to observe distant galaxies and black holes, offering a window into the deepest reaches of the cosmos. The dual nature of light, behaving both as waves and particles, was further illuminated by the advent of quantum mechanics. Light, as photons, exhibits properties of both waves and particles, a concept encapsulated in the wave-particle duality. This duality is a cornerstone of quantum theory, explaining phenomena such as interference and diffraction. James Clerk Maxwell's equations describe light as oscillating electric and magnetic fields propagating through space. These electromagnetic waves travel at the speed of light, carrying energy across vast distances, from the sun to Earth and beyond. Modern science continues to probe the nature of light. The LIGO Observatory's detection of gravitational waves confirmed Einstein's predictions, revealing ripples in spacetime caused by cataclysmic cosmic events. Telescopes and other instruments allow us to capture light from the furthest reaches of the universe, providing insights into the early moments of creation. As we travel on a beam of light, we traverse the boundaries of classical and quantum physics, encountering the profound implications of relativity and the mysterious nature of the cosmos. Light, in all its forms, remains a fundamental key to unlocking the secrets of the universe. The vastness of space seems to stretch endlessly, a boundless expanse of nothingness. Yet, as we have come to learn, this apparent void is far from empty. The cost of free space lies in the complex interplay of forces and particles that give structure to the cosmos. The early 20th century brought groundbreaking insights into the nature of space. Albert Einstein's general theory of relativity, of course, revealed that space and time are intertwined in a dynamic fabric known as space-time. Massive objects warp this fabric, creating what we perceive as gravity. In Einstein's universe, free space is not a passive backdrop, but an active participant in the cosmic dance. The curvature of space-time around massive objects like stars and planets determines the gravitational forces we experience. This warping of space-time is a fundamental aspect of the cost of free space. At the quantum level, the concept of free space takes on an even more intriguing character. Quantum field theory posits that what we perceive as empty space is actually a seething foam of activity. Virtual particles constantly pop in and out of existence, a phenomenon known as vacuum fluctuations. These fleeting particles, though temporary, have measurable effects. They contribute to the forces and interactions between particles, shaping the very fabric of the universe. The energy associated with these fluctuations gives rise to the notion that even the emptiest vacuum has a non-zero energy, referred to as vacuum energy. One striking manifestation of vacuum energy is the Casimir effect. When two uncharged, parallel plates are placed extremely close together in a vacuum, they experience an attractive force due to the vacuum fluctuations. This effect demonstrates that free space has tangible, measurable properties. The concept of vacuum energy extends to cosmology, where it plays a critical role in our understanding of the universe's expansion. Dark energy, a mysterious form of energy permeating space, is believed to be driving the accelerated expansion of the universe. This dark energy is a form of vacuum energy, representing the most significant cost of free space on a cosmic scale. As we ponder the cost of free space, we are reminded that what appears to be nothing is, in fact, filled with dynamic forces and energies that shape the universe. The interplay of relativity and quantum mechanics reveals a cosmos where even the emptiest regions are rich with activity. Modern scientific instruments continue to probe the depths of space, uncovering the hidden costs and energies that define our universe. The Higgs vacuum and the void. At the heart of modern physics lies the Higgs field, an invisible entity that fills the entire universe. Discovered through theoretical insights and confirmed by experiments, the Higgs field plays a crucial role in the standard model of particle physics. The journey to understanding the Higgs field began in the 1960s when physicists, including Peter Higgs, proposed a mechanism to explain how particles acquire mass. This theoretical framework suggested that particles interact with an all-pervading field, the Higgs field. The theoretical predictions culminated in a momentous discovery at CERN's Large Hadron Collider in 2012. Here, scientists observed the Higgs boson, a particle that signifies the presence of the Higgs field. This discovery confirmed the existence of the field and validated decades of theoretical work. But what does it mean for particles to acquire mass? Imagine the Higgs field as a vast, invisible ocean. As particles move through this ocean, they interact with it, gaining mass in the process. Some particles, like photons, glide through effortlessly and remain massless, while others, like quarks and electrons, experience resistance and acquire mass. The Higgs field is also associated with a unique energy landscape. The field's value is not uniform but varies across space, creating a potential that determines how particles interact with it. This potential is fundamental to the stability of matter and the structure of the universe. In the early moments after the Big Bang, the Higgs field played a pivotal role in shaping the universe. As the universe cooled, the field settled into its current state, imparting mass to particles and enabling the formation of atoms, stars, and galaxies. This phase transition was crucial for the development of the cosmos as we know it. Today, the Higgs field remains a focus of intense research. Scientists continue to explore its properties and implications, using advanced particle accelerators and detectors to probe deeper into its mysteries. Understanding the Higgs vacuum offers insights into the fundamental nature of reality and the forces that govern the universe. The Higgs field, an invisible yet omnipresent entity, shapes the very essence of matter and reveals the profound interconnectedness of all things. In the 21st century, our quest to understand nothingness has led to remarkable breakthroughs. Advances in technology and experimental techniques allow us to probe deeper. Another intriguing idea is the multiverse theory. This hypothesis suggests that our universe is just one of many, each with its own physical laws and constants. These parallel universes may exist within a vast, overarching space, adding layers of complexity to our understanding of the void. Black holes provide another window into the mysteries of the void. At the event horizon, the boundary beyond which nothing can escape, space and time behave in extraordinary ways. Stephen Hawking's prediction of Hawking radiation, particles emitted from black holes, suggests that even these seemingly empty regions are rich with quantum activity. The study of the cosmic microwave background radiation, the afterglow of the Big Bang, offers insights into the early universe's conditions. Tiny fluctuations in this radiation reveal the seeds of galaxies and clusters, highlighting the critical role of the vacuum in the universe's formation and evolution. We recognize that what we once considered empty space is in fact a complex and dynamic entity. The interplay of dark energy, quantum fluctuations, and potential multiverses paints a picture of a vibrant, ever-changing cosmos. Modern research continues to push the boundaries of our knowledge. Particle collisions at accelerators, observations from space telescopes, and sophisticated simulations all contribute to our evolving understanding of the void. Each discovery brings us closer to comprehending the fundamental nature of existence. The insights shared here are drawn from Frank Close's book, Nothing, a very short introduction. I've tried to present the concepts as clearly and logically as possible, though I'm aware it might not be perfect. For those of you interested in a more in-depth exploration, I highly recommend reading Close's work. It's a fascinating dive into the nature of nothingness. I'd love to hear your thoughts on these ideas. What did you find most intriguing? Were there concepts that surprised you? Feel free to share your reflections in the comments. Until next time.